people are here. Okay, so we want to go to speaker view and choose me so I can see what I'm doing. And we're going to go to solving triangles. And number 8 was the question. And
So
the problem, yeah.
The problem, or the one I'm having trouble with, is where it says using the law of cosines again, find cosine of b is equal to cosine of beta. I got 0.74787 and I got beta correct. So like I don't know what I'm doing wrong to get that wrong, because I got all the other ones right. I just didn't get that one correct.
Okay, well let's take it from the top so I can be oriented as to what we're doing.
Okay.
And let's see what one. This is okay. Here you go. Last time. And let's switch over to the workbench view. Mouse. Here. And so triangle ABC, if angle A is 44 point, now you're going to have different numbers, right? I think it's parameterized, right? So either you can give me your numbers.
Yeah, I'll give you my numbers.
Okay.
So alpha is equal to 33.2 degrees, right? And then b, the little b, is equal to 9.7 inches. And then little c is equal to 14.1.
Okay, so there's our givens. And so this looks like angle, side angle, side, right? Because alpha would be opposite angle A, or angle A is alpha, and the side opposite that we don't know, that would be A. So we know the adjacent side. So let's draw something like that with 9 point, doesn't really matter which one is B and which one is C. So let's say this is 9.7, this is 33.2 degrees, and this is 14.1. So this is a side angle side situation where we want to use the law of cosines because we don't have a side with its opposite angle. We don't have a pair, angle opposite side. We don't know any pair like that, right? So we want to find, this is going to be A, this is point A, I guess this must be B and C then, right? And so A squared is, well, in general, B squared plus C squared minus 2BC cosine A. And so that's going to be 9.7 squared plus 14.1 squared minus 2 times 9.7 times 14.1 times cosine of 33.2. And we want to make sure we're in degree mode. So let's go to our calculator and turn it on and say, what mode are we in? We're in degree mode. Good. So let's clear this out and say, you know, it's almost like we want to have a formula, right? So we can say, let's see if this works. So if we say little a, then we say equals, and then we say, yeah, we can't use little b. I think that's a reserved variable name. So let's say we're dyslexic and we think b is d. So we're going to say alpha d squared plus, I think we can use c minus 2 times b times c times cosine Error reserved. Which one? It doesn't say. Can we go to the variables and just select all? And can we just delete them? Clear. Okay. Oh, it didn't actually. I would like to blank. Okay, there's nothing there. So, you know, I guess capital A and capital B that are being currently used for, you know, real numbers, and I think they're at my disposal. But are there other variables that we can't? So A, B, C. Oh, it looks like C is being used, right? What is C? Okay. All right, let's just not bother. Okay, so 9.7 squared plus 14.1, I believe it is. Yep. Minus 2 times 9.7 times 14.1 times the cosine of 33.2. Okay, so that's going to be the square of A. So if we want A, we're going to take its square root. So here's the square root operator, and I'm going to say that last answer is about 8, pretty close to 8. So they say accurate to 4 decimal places. I guess 8.007, 0007, 0007. Oh, that's A. They want the square of A, right? Okay.
Right, and then the other one is 2 decimal places.
Okay. So if let's see, I want to go. What are we looking at? Oh, we're looking at the calculator. So let me take the calculator out of production. Say this is 64.0115 to the nearest 10,000th, right? This A, and this, we could just go 8.00. Using the law of cosines again, okay, so cosine of B, huh? Well, this is kind of where your question is. So really, we want to use, I mean, I would use the law of sines at this stage, right? Because we have a pair, you know, we know A and the angle A, right? So I would tend to want to go with that. But since they say law of sines, yeah, I mean, law of cosines again, let's write that out. So here is, the mouse disappears. Okay, so B squared is A squared plus C squared minus 2 times A times C times cosine of B. And we would solve for B. Well, let's solve first for cosine B and get A squared, yeah, plus C squared minus B squared all over 2AC. And so then B, well, let's see what is that. Okay, so the nice thing about the TI-86 that is not true on the 85 is that you can get the previous answer. Right, so if I say second entry, that's not what I want. I want the one before that. So I say it again, and then it computes this value again, right? Which turns out to be 64. So maybe, do I want to store that in something? I'm going to store it in the variable name AS. short for a squared. Oh, I wanted to put an S there, and there we go. So now if I say, tell me about AS, I think I have to say alpha again, right? Yeah. Yeah, then it remembers it. Okay. So, so I want a squared plus c squared. Okay, that's going to be this thing plus c squared is 14.1 squared, right? Minus b squared, which is 9.7 squared. Okay, so that's the numerator. And I think I want to compute, I didn't put parentheses around that. Let's go ahead and insert a parenthesis. You can do this, right? So we can go second delete, and that puts it in insert mode, and we can insert a parenthesis there, which we kind of need, don't we? All right, then we go back to the end, and we're going to say divide that by, in parentheses again, right? Because order of operations. 2 times a. Now a was 8, right? 0.000 something. Is there a 7 there or something?
0.0007.
Yeah. I don't think we really need that, but let's go ahead and throw it in for good measure. Times c, which is 14.1. Close parenthesis. So this should be the cosine of b. So this should be a number between -1 and 1. It's a positive 0.7479. And as such, we should be in this first quadrant, which kind of makes sense. B looks like to be a pretty acute angle, right? So we want the inverse cosine of that, right? And let's store that into a variable b. So I got 41.59, and how much accuracy do they want? 5 decimal places? That's a lot of decimal places. All right, well, let's so I got 41 point, and this should be in, oh, this is the cosine, right? Okay, so the cosine in 5 decimal places is 0.74786, and that's 5.
Yeah, I just plugged that in and it said that was correct.
Okay.
So when I multiplied it, I didn't put the 0.0007. I just.
Oh, really? So
yeah.
It made a difference, right?
It was like a very minute difference. So,
yeah.
Yeah.
Yeah, it's a slippery business, these significant digits.
Yeah, I wouldn't imagine them to make such a difference. But
right. Okay. So thus beta, and they want these to 2 decimal places. Yeah, when they ask for 5 decimal places, you kind of want to be careful. That's a lot of decimal places. So beta is 41.59 to the nearest hundredth. And finally, the sum of using the sum of the interior angles, right? So we're going to have 180 minus 41. So I'm going to say 180. Should we turn on the see what I'm doing? 180 minus b, where I stored this value, minus, what is it, 33.2. So that's good. This could be an obtuse angle. Huh? Yeah, this is obtuse. Okay, so that's 105.2 decimal places. So 105.21, I guess. And we'll submit that because resistance is futile, and they're all wrong.
Well, you have different values than me.
Oh, of
That
course.
could be why.
Thank you. I was thinking,
But those are
wow.
all correct answers for me, at least.
Okay, right. Yeah. I didn't use the given information, did I? Okay. Right, but it's the process that counts. And so it turns out, yeah, very sensitive to that last little decimal place. That's why, on calculators, I often, take all the digits I can get until the very end and then round, not round as you go along, because these rounding errors cascade. And so that's why I try to use the memory to store numbers into memory locations and then recall those locations. So you can do it that
Thank you,
way.
Professor, for going over that.
Sure, glad to. Any other requests? Yeah, these are pretty good. There's a lot of these, 20 of them, right? There's also 20 problems on the chapter 6 test, which is due Monday. So it gives you plenty of time. And there's also homework about ellipses. So let's talk about ellipses. Okay. Here's a funny thing. Ready to it. So there's ellipse, right? A plain closed curve, in popular language, a regular oval, which may be defined in various ways. Considered as a conic section, the figure produced when a cone is cut obliquely by a plane making a smaller angle with the base than the side of the cone. So it cuts across the cone. A curve in which the sum of the distances of any point from any two foci is a constant quantity. Right, that's a good one. And the planetary orbits being approximately elliptical. Ellipse is sometimes used for the orbit of a planet. But look at what happens when I change the last two letters of the word to ellipsis. Well, ellipse is now rare. So what are ellipses? Conical section. Okay, so this is the rare definition. The omission of one or more words in a sentence which could be needed to complete the grammatical construction or fully to express the sense. Formally used as the name of the dash employed in writing. Right, so ellipsis is generally ... That's what most people think of when you think of ellipsis. With an I, because that's a completely different word, although apparently there is some historical connection with the ellipse. Okay, so I guess we want to be here. And let's look at our derivation that we left off with yesterday, right? So we said, yeah, ellipses, here's the geometric definition of ellipse, the set of all points, the sum of whose distances from two fixed points, the foci, is a constant. So we said, yeah, okay, if you got a point x, y in the plane, and it's at a distance d1 from the first focus and a distance d2 from the second focus, then we want the sum of those distances to be a constant. And we choose to make that constant twice a. Well, we haven't really seen why we chose twice a, but we then use the distance formula together with the coordinates of those points. So xy to negative c0, that distance is given by the distance formula here, and xy to positive c0, very similar sort of expression. And so we have the sum of two complicated radical expressions is equal to twice a. And you isolate one of the radicals using subtraction property quality, subtract one of the radicals from both sides, and you've isolated one of the radicals. Then you can say if these numbers are equal, then their squares are equal. And we get a bunch of terms that cancel out. We isolate, so we're down from two radicals to one radical. We isolate the remaining radical and say if these things are equal, then their squares are equal. And we get then an equation with no radicals. And after the dust clears, Turns out that equation is equivalent to this equation in the box. Okay, so let's rewrite that over on our sheet here. I guess I'll go use this. I'm just trying to get short on paper, so let's go ahead and use this bottom sheet here. So we have x squared over a squared plus y squared over a squared minus c squared is equal to 1. And the picture we have in mind is something like this. That we have a foci, let's say, here, and another one here, and we have a point. Well, let's say if the point is on the y-axis, that's a particular, so this distance is c, and the sum of these distances, and these distances are equal, right? Since this is on the y-axis, and the points on the y-axis are equidistant from, well, maybe I should label the point C. The edge has length C because it's from 0 to C on the x-axis, right? So let's label it that way, right? So this plus this is 2a, and these are the same, so each one of these must be a. Right, so we have a little right triangle here. We know this leg is C, this leg is A, so what does that make this leg? By Pythagoras, so we know that, let's call that leg B, okay? Then we know B squared plus C squared is equal to A squared. That's the Pythagorean relationship there, right? And yeah. So guess what? Oh, lost my blood. And so what does that mean B squared is? Well, B squared is A squared minus C squared, right? Oh, well, that's what we got in our diagram here. So if we rename this B squared, then we've got a very simple looking equation for the ellipse, right? X squared over A squared plus Y squared over B squared is equal to 1. It's the very picture of simplicity. Now, if A equals B, then C is equal to 0, right? And so the ellipse then collapses into a circle. If A equals B, then that's the radius of a circle, and you get the equation A squared plus B squared equals R squared, right? That's a circle of radius R centered at the origin, where R would be, you know, A and B, right? A equals B, so R equals A equals B, right? So that's a special case. When A equals B, this is the equation of a circle of radius A or B centered at the origin. So, and that's kind of nice, right? Because if you think back to what we learned about transformations, you can stretch horizontally by replacing x by x over a, or you can stretch vertically by replacing y by y over b, right? And so this is sort of like if you took the unit circle and replaced, so, you know, so recall x squared plus y squared is the unit circle, right? So if you replace x by x over a and y by y over b, that's going to stretch horizontally by a factor of a, and it's going to stretch vertically by a factor of b. And, you know, if you were to stretch the unit circle, you'd get an ellipse, right? An oval shape, right? So that sort of corresponds to what we know about the unit circle and transformations. So what other kind of transformations can we do? And this gets us right into section 4 of chapter 6, I think, which is transformations on conic sections. So what happened to chapter 3? Well, I think section 3 of chapter 6 is the hyperbola. The hyperbola, very similar to the ellipse. You just change this plus sign to a minus sign. The geometric definition of the hyperbola is the set of all points in the plane, the difference of whose distance is from two fixed points is a constant. So now, since the sum of the distance, it doesn't matter which one you add first. The ellipse is a little bit simpler. Now you've got a major axis and a minor axis, right? So your book does a funny thing, which, you know, I guess I'm kind of used to it now, but the Stewart text, so let's say in Stewart, A is always bigger than B. So if the bigger number, so you may have x squared over b squared plus y squared over a squared. I know alphabetically incorrect, right? Well, a should go with x because a comes before b. Well, so if you have this, then the major axis is on the y-axis, right? Major axis vertical, right? So what does that look like? Let's say we have the equation x squared over 4 plus y squared over 9 equals 1. Then what are the intercepts? Let's make a table of values for this, okay? If x equals 0, then you have y squared over 9 equals 1, right? And those are the y-intercepts. And so what values of y will make y squared over 9 equal to 1? Well, y squared would have to be 9. And so plus or minus 3, right? Those are the y-intercepts. What are the x-intercepts? Well, if y equals 0, you kind of play the same game, right? X squared over 4 equals 1. X is plus or minus 2. So if we start by plotting the intercepts, let's say 1, 2, 3 is the y-intercept here, and negative 1, 2, 3 here, and 1, 2 are the x-intercepts here and here. So this is 3 and negative 3. This is 2 and negative 2. Can we draw an oval through those 4 points? Sure. Just kind of fake a oval-shaped curve right through these points. So where are the foci? They're on the major axis, which is the longer axis, right? So the major axis is from 0, negative 3 to 0, 3, or the other way around. It's this line segment here. That's called the major axis. The semi-major axis is from the origin to 3, so that's half of the major axis, right? The minor axis is from negative 2, 0 to 2, 0, right? So that's this axis. The foci are on the major axis. So in this case, the foci are above and below the origin, right? And how can we find the major axis? We'll go back up here to this relationship between A, B, and C, right? C squared is A squared minus B squared. So it's the bigger one minus the smaller one, which is another reason to say A is the bigger one. Then you don't have any confusion about the formula. So C squared is equal to A squared minus B squared. The bigger minus the smaller will be positive, and that's good because C squared has got to be positive, right? So that's going to be 9 minus 4 is 5. And that means that C is square root of 5, which is about 2.45, I think, something like that. And so that's going to be up here and down here. Okay, I made the axis too thick so you can't really see, but yeah, square root of 5 up here and negative square root of 5 down here. Those are the two foci, right? All right, or if you were to say x squared over 9 plus y squared over 4, then this would be rotated 90 degrees, right? And you'd have an ellipse with the major axis on the x-axis. Okay, I think that's, oh, there's one other thing. There's something called the eccentricity of the ellipse. So definition, the eccentricity, that's the word we're defining, is a over, I'm sorry, it's a number between 0 and 1. The closer to 1 it is, the more eccentric it is. The closer to 0, the more circular it is, right? And it's going to be the smaller number divided by the bigger number. The bigger number is A, right? The smaller number is C, so it's C over A. That's a definition for X. So that's a description of how eccentric it is. If C is 0, then it's a circle, right? And so a circle is an ellipse with 0 eccentricity. If the eccentricity is 1, well, then it's not really an ellipse either, right? It's just going to be sort of a line segment. So it's so extremely eccentric that it collapses into a line segment. Okay, so let's do some exercises. So do we have the textbook handy somewhere? Let's see. Yeah, we do. Okay. So let's bring that up. So yeah, we kind of did all this yesterday. Great. So let's skim over that. We see that we arrived at this equation. For convenience, let b squared equals a squared minus c squared. It's more than convenience, right? It's b is then an important parameter. It's the length of the semi-minor axis, right? B is the smaller one, A is the bigger one, right? So the length of the major axis is twice A, and the length of the minor axis is twice B. The length of the semi-minor axis is B, right? So it's more than just a point of convenience. It's actually a pretty descriptive parameter. Okay, so they talk about finding the intercepts. And they draw this triangle here, right, with A, B, and C, right? A being half the sum of the distances to the foci from any point, right? And B being the length of the semi-minor axis, C being the distance to the focus, and A is also, right, so if you think of this as like a ladder leaning up against a wall, if that ladder were to slide down so it lies on the ground, it would go from the origin to this point A, right? It has length A, right? So it's kind of like you slide that up so it meets there, and then the base will be at the focus. So equations, so the ellipse with the center at the origin. And notice that they say that A is always greater than B, right? So it wasn't my way of thinking before I read this book, but it doesn't have to be your way of thinking, but it is kind of a convenient rule. So then it's sort of like A doesn't necessarily go with X, A is the bigger one. So sketching an ellipse, and notice I got the planets out here, right? It's the shape of the orbit of a planet is an ellipse, and you can prove that from Newton's laws. You can get Kepler's laws. Yeah, save that for physics, huh? I think actually Kepler's laws are in here somewhere, but finding the foci of an ellipse, so we kind of did that, right? You got this relationship that b squared plus c squared equals a squared. A is the bigger one, right? And so the eccentricity of an ellipse, we define that to be c over a. All right, so that's got to be a number between 0 and 1, right? If it's close to 1, then C is almost equal to A, and the ellipse is an elongated shape, right? So this is a large eccentricity here. If C is small, then it's mostly circular, or approximately circular. Right? Oh, there's some discussion of gravitational attractions causes the planets to move in elliptical orbits around the sun with the sun at one focus. This remarkable property was first observed by Johannes Kepler and was later deduced by Sir Isaac Newton. They just call him Isaac Newton because we're Americans. We don't recognize this royal lineage. Just as an aside, what the hell? It's like the 21st century. Do we have to have royals running around? I just find that annoying. Okay, I'll get off my soapbox. You know what? Let me get back up briefly. What's his name? Hawkins, the wheelchair guy who suffered Lou Gehrig's disease or something.
Yeah, Stephen Hawkins. Something like that.
Stephen Hawkins. I think you're right. Yeah.
Or Stephen. I don't know. Something.
Stephen
like that.
Hawkins, something like that. Anyway, they offered him a night ship and he refused it. A great moment in royal rejection. Okay, so ellipses like hyperbolas have an interesting reflection property that leads to a number of practical applications. If a light source is placed at one focus of the reflecting surface with an elliptical cross-section, then the light will be reflected off the surface to the other focus. You sometimes experience this in buildings, right? And also in lithotripsy, basically that means, getting rid of kidney stones. So you focus energy from outside the body, inside the body by putting you in like an elliptical container, right? Where the source of energy is at one point and your kidney stone is at another point, and they dissolve the kidney stone that way. So that's this idea here, right? Any energy emanating from one focus reflects off the ellipse, and they all bounce off the outside. So if you have energy emanating outwards, let's say from F1, it will bounce off the ellipse here, there, and everywhere, and then refocus at the other focus. That's why it's called the focus. All right, I think we're ready for some exercises. Let's see, can I move this up? Okay. Yeah, what do they say in these first few ones here? Okay, it's over here. Graphs of ellipses. Match the equation with the ellipse in question, right? So how about this one? What can we say? That the major axis looks to be about, well, 1 point something. So well, let's go ahead and just graph one of these things, right? So how about 7, right? It's not in standard form, is it? Right? How can you tell whether it's in standard form or not? Well, you should have a sum of squares of x and multiples of x squared and y squared adding up to 1, right? And so if you don't have 1 on the right side, you can divide both sides by 4 here, and then you'll have it in standard form, right? In the standard form, you always have 1 on one side of the equation. It's the one side, because there's 1 there. Okay, so let's go to our bench here, which is, I guess okay. So I'm gonna, so they have an equation, x squared over 16 plus y squared over 4 equals 1. So this is number 5. And they want us to, let's just do a quick sketch of each one of these, okay? So x squared over 16 plus y squared over 4 equals 1. So what's A? A is the bigger one, and that's the square root of 16, which is 4. And B is going to be the square root of 4, which is 2, right? And so what's C? Well, C is the square root of A squared minus B squared. And so that's going to be the square root of 12, huh? Which is 2 times the square root of 3, or approximately 3.4 something. Maybe 3.5, I don't know, somewhere in there. 1 point, yeah, I think it's closer to 3.5. Huh? And so what does a graph of that look like? Well, the major axis is horizontal, and it goes from -4 to 4, right? So here's 1, 2, 3, 4. Here's -4. Here's 4. And those are the x-intercepts. The minor axis is vertical. It goes from -2 to 2. And the 1, 2, 3. So the foci are, it's pretty eccentric, right? They're way over here towards the ends. And so the ellipse looks like that, roughly speaking, right? Any sort of reasonably oval shaped thing will do here. And don't forget to label your axes. Okay. So what's number 6? This is y squared, x squared plus y squared over 9. I'm running out of graphite again. This is bad. Really? God, it's amazing to me how much they make you waste. Look at the size of that thing. More though in the reservoir, I think. Okay. So x squared plus, what is it, y squared over 9 is equal to 1. So here A is equal to 3 and B is equal to 1, right? A has got to be the bigger one in the tradition of Stewart, right? And so that implies that C is equal to the square root of 9 minus 1, right? Which is 2 times the square root of 2, the square root of 8, right? It's twice the square root of 2, and that's about 2.8. Right, square root of 2 is 1.414, so 2.828, something like that. And this will have the major axis vertical, right? So let's draw it like this. Here's 3 and -3, let's say, is here on the y-axis. And here's 1 and -1. So our ellipse would look like this, with the foci very, very close up to the y-intercepts there, right? Okay. Then number 7 here is 4x squared. So this was number 6, and here's number 7. 4x squared plus y squared equals 4. You'd want to put that in standard form, right? Right? So A is the bigger one. That's going to be 2. B is the smaller one. And, you can think of that as over 1, right? So B is 1. And that implies that C is the square root of 3, right? The square root of 4 minus 1, which is about 1.7. Okay, so again, the major axis is vertical. And we're going to go from, let's say, here's 2. Now let's put 2 here. And this is the y-axis and the x-axis. And let's see, so if that's 2, then 1 would be about here if we use the same scale for x and y. And the major axis is vertical, so our ellipse like that. And 1.7 is going to be, pretty, again, these are pretty eccentric, right? So what are the eccentricities here? This one has E equals C over A, right? And that's going to be twice square root of 3 over 4, or square root of 3 over 2. So about 0.866, right? That's a nice trig number. So that's pretty eccentric. And here the eccentricity is twice square root of 3 over 4, which is going to be square root of 3 over 2. It's got the same eccentricity. And here the eccentricity is twice square root of 2 over 3, which is going to be about 0.93, something like that. Even more eccentric. No, lets its fingernails grow to a ridiculous length. That was the story, if you're wondering what I'm talking about. Who's the spruce goose guy? Hewlett? No. Eccentric billionaire from the 60s. Never mind. So number 8, one more of these. We've got 16x squared plus 25y squared equals 100. So in this case, we divide through by 100. Did I get that right? 16? Yeah. Oh, it's 400. Sorry. Okay, so I think that's going to reduce. Does 16 go in evenly here? Yeah. 25, huh? So, right. So this is 8, 16, I think 16. 16 times 25 is 400, right? So, yeah. So after dividing through by 400, we get that. So that means that A is 5, and B is 4, and C is the square root of 9. So that's 3, right? Oh, good. So we get a little 3, 4, 5 triangle there. What would the graph look like? Well, the major axis is horizontal. So we're going to go from 2, 3, 4, from -5 to 1, 2, 3, 4, 5, and 4, and -4. And so this one is not quite so eccentric, it looks like, right? There's a reasonably oval shape through those points. And where's the focus? It's at 3, right? On the major axis. So this is -3 and 3. And you see this 3, 4, 5 triangle in here, right? This is 4, this is 3, and that's 5. That's, A. It's 5, right? And so when we look at these in the book, which is here, let's see, yeah, this is that 3, 4, 5 one we just did. This is the 9 and 1, right? I forget which one was which, but you kind of recognize these are. What's this one here? I guess A is 2, huh? Yeah, and B is 1. It's It's y squared over 4 plus x squared equals 1, right? That one. And this one, yeah, the intercepts were 4, plus or minus 4 on the x-axis and plus or minus 2 on the y-axis. Okay, so we've kind of been over the graphing of ellipses. You know, if it's not in standard form, put it in standard form, then find your A and B and C, find your intercepts and sketch a graph, right? Okay, so let's say we're good with the ellipse. There's the ancillary circle that fits inside the ellipse, okay. There's various applications, right? There's quite a few applications. The plywood ellipse, then there's the flashlight ellipse, just like there was a flashlight. Flashlight makes a cone, and so these are all conic sections. So depending on what angle you hold your flashlight at, the oval or shape of the light will be either, have a parabolic edge if it's parallel to the side, or if it cuts across, it'll be an ellipse, right? Okay, so let's talk about the hyperbola. All right, so here's the geometric definition of the hyperbola. The set of all points in the plane, the difference of whose distances from two fixed points is a constant. These two fixed points are the foci of the hyperbola. So notice the shape of the hyperbola is quite a bit different. So this, if you're cutting the cone parallel to the axis of the cone, but not through the center, then you'll have, it's a two-sided cone, right? So one side of the cone will be cut this way, and then you'll have sort of the mirrored image on the other side. And we can do the same thing with, I'm not going to drag you through that again, but you use this, the difference of the distances is a constant. And they say plus or minus a, right? Because depending on which one you subtract from which, you may get a positive or a negative. So you get two radicals, you have to isolate a radical and square both sides. They say proceeding as we did before, we simplify this to that. All right, that might be a good exercise for you. And then we get down to this, where b squared is equal to c squared minus a squared. So that's a different b squared, right? For the ellipse, we had b squared was a squared minus c squared. And here now that's the reverse of that. The reverse of that difference, right? Okay, so we have the two branches of the ellipse. We have the transverse axis of the parabola. And they're going to show us that here. So when you're graphing an ellipse, you're going to get asymptotes, right? The transverse axis is this line segment connecting negative a to a, right? And again, we associate a with the first term, regardless of whether that's an x squared or a y squared, right? So in this equation, it's x squared over a squared is the first term, and this one is y squared over a squared is the first one. And that's going to be the one that has the intercepts, right? So notice that there are no y-intercepts here, and there are no x-intercepts here, right? So depending upon which flavor of hyperbola you've got, just like there are two flavors for ellipse, right? Depending on whether the major axis is vertical or horizontal. Here, the transverse axis can be vertical or horizontal. But what a feature of an ellipse that we don't have, a feature of the hyperbola that we don't have on the ellipse are these asymptotes, right? So as x gets large here, y approaches this line, b over a times x, or this line, depending on which way you're going, right? If x is going to negative infinity, then y is approaching negative b over a times x, approaching that line. All right, so yeah, I mean, this is pretty complicated stuff. And it definitely takes some practice to get accustomed to it. But let's do a little, how to sketch a hyperbola. So you draw the central box. Now this is a box which is going to be 2a wide and 2b tall, or the reverse of that, right? It could be 2a tall and 2b wide. Once you have the box, see the box? right? It's 2a wide and 2b tall here. Then you draw the diagonals of the box, and those are your asymptotes, right? And then you got the vertices at plus or minus a, either on the y-axis or the x-axis. And those are the vertices of your hyperbola. And then you just draw the branches asymptotic. Make sure that when you draw them, you do get closer to the asymptote as you go out here, right? Don't go away from the asymptote. You want to approach the asymptote, right? So then we have vertices, foci. Yeah, we also have foci, right? C squared is equal to a squared plus b squared in this case. It's the bigger one. So, it's hauntingly familiar to the ellipse, but different, right? And so comets, some comets take a hyperbolic orbit, so you only ever see them once. They come in and they go out, they don't come back. Other comets follow an elliptical orbit, so they come in towards the sun, they go very fast, and then they go out here into outer space, but then they come back. So there's two flavors of comets. So with having said all that, there's the reflection properties again, similar to the, but let's draw a few hyperbola, right? So, and go through the process of doing that. So let's use this space here. I know we're going kind of a little fast because this is the end of week 14, and we've got a certain amount that you need to say we talked about. Sorry if it's a little uncomfortably fast. So in the text, we see this is now 11.3, number 4. They want us to sketch a graph of x squared over 16 minus y squared over 9 equals 1. Okay, so now this, you can tell it's a hyperbola because we're subtracting, right? With an ellipse, you're adding squares or multiples of squares. With a hyperbola, you're subtracting multiples of squares and getting 1, right? So we can see A here is 4 and B is 3. So what does that mean about C? Well, in this case, C is equal to the square root of A squared plus B squared. Yeah. So that's a plus instead of a minus. For the ellipse, we had a minus here, right? Which means that C is bigger than both A and B. And in this case, C is equal to 5, right? 16 plus 9 is 25. I keep losing my earbud here. Okay, and so when we draw the ellipse, here's the y-axis. That's going to be the one with no intercepts, right? If y is equal to 0, then x can be plus or minus 4, right? So let's draw in 1, 2, 3, 4, and 1, 2, 3, negative 4. So the box will go from -3 to 3 on the y-axis, right? These are not intercepts though, right? These are the intercepts. These are the vertices of the hyperbola. So these things are useful for drawing the asymptote though, right? So we make a little 6 by 8 box here, centered at the origin. And we draw in the asymptotes. Where's my straight edge when I need it? I've got a long straight edge, but I want the shorter one. Yeah. So we line up the corners of the box and draw the asymptote. And there's another one here. Conic sections, people. Very deep subject. I have a book just on conic sections, which is, I can't put my hands on it right now. I think it's not here, but pretty deep subject. So we're just sort of skimming the surface a little bit here, right? But we want something that's, following the asymptote and then diverging slightly to pick up the intercept and then going off in the opposite direction. approaching the asymptote, right? Same thing over here, mirror image, right? Okay, and that's the hyperbola. This is the y-axis and the x-axis as usual. So can we compute some points on the hyperbola? Here's 4, 5, 6, 7. Let's say if x is 7, then what are the points on the hyperbola? Well, we can plug into the equation. So we can say if x equals 7, then the equation becomes 49 over 16 minus y squared over 9 equals 1. Solve for y. Sure. So 49 sixteenths minus 1 is going to be 33 sixteenths. So y squared is equal to 9 times 33 over 16. Can we reduce that? Do we care? I guess it's 293 over 16, which is approximately what? 1 to 10, leaving 133. Yeah, 128. So 5. So yeah, sorry, this is going to be a 3. So about 18.3. That's going to be y squared. So y is the square root of 18.3, which is going to be 4 point something. Let's say 4.2 or something like that, 4 point something. So here's 4 point something is here. Yeah, that's about right. Yeah, or negative, right? Plus or minus. So we could also be down here at 4 point something. And yeah, about there. Okay. 4.3, 4, something like that, 4.4 maybe. That is a sketch of the ellipse. Now, let me tell you one more thing before we wrap up week 14. And, well, 2 more things. Okay, sorry about this. I know this is a lot. But, one more thing is that we can shift, right, horizontally. Shifted conics, right? So you replace x by x minus h and y by y minus k, and you will have shifted your conic so it's no longer centered at the origin, but it's the same shape, right? Shifting doesn't change the shape, it just changes the position, right? So if we've got, let's say, x minus, I don't know, 3 squared over 4 plus y minus 2 squared over 9. So what's A? A is 3, right? And B is 2. Where's the center? The center is at 3, 2. Oh, that's interesting. Yeah, that's a coincidence. Should we put it somewhere else? Here, we can change this to a 5, let's see. Okay, so now the center is at 3, 5, right? So that's in the first quadrant. So if we were to sketch this, we would emphasize the first quadrant quite a bit, right? And so let's say here's 1, 2, 3, and 1, 2, 3, 4, 5. This is the center point. It's not a point on the ellipse, right? But the major axis goes with y, so it's vertical. So we're going to go 3 up from the center to get to the top, and 3 down from the center to get to the bottom. The minor axis, the semi-minor axis has length 2, right? So we're going to go 2 to the right and 2 to the left. So that gives us the 4 extreme points on our ellipse, and we can just fake in an oval with those 4 points, right? Oh, well, yeah, this is the y-axis is over here. So where are the foci now? Well, c is equal to square root of 9 minus 4, which is square root of 5 here, right? Which is about 2.45. And so you're going to go up 2.5 and down 2.5 approximately to find the 2 foci. Here's the one other thing. It's now 12:07. So recall that cosine squared theta plus sine squared theta is 1, right? So we're back to trigonometry. Hooray! Full circle, or full ellipse, maybe. Here we've got a sum of squares equal to 1. Oh, I didn't write the 1, did I? Sorry. It's not an equation without an equal sign, is it? All right, so I would like this to be, say, cosine squared, and this to be sine squared. Then cosine squared plus sine squared equals 1, right? So let's do that. Let's say, okay, cosine squared theta is going to be the x minus 3 squared over 4, and sine squared theta is going to be the y minus 5 squared over 9. Can we solve for x and y in these? Sure. Right? So we can multiply both sides by 4 and then take square roots, and we'll have x minus 3. Let's take the positive square root, emphasize the positive. It's going to be that. Right? Similarly, y minus 5 is going to be 3 sine theta. So x is 3 plus 2 cosine theta. So what is that? That's a sinusoid with an equilibrium at 3 and an amplitude of 2. Right? So as you go around the ellipse, what does x do? Well, it centers around, oh, sorry. Yeah, x. It's centered around 3, right? X oscillates back and forth as you go around the circle with the ellipse, right? X is going to oscillate between 1 and 5, right? So this is the point 5, 5, and this is the point, 5, 1, right? Oh, sorry, 1, 5. So, the equilibrium is 3, and we're oscillating with amplitude 2 around a center point of 3, right? And as theta goes from 0 to 2 pi, we'll go on once around the ellipse. Similarly here, y has an equilibrium of 5, right? With the center of the y is 5, and it oscillates with a amplitude of 3. Right? So we go up and down 3 from y equals 5. So when theta equals 0, where are we? So we can make a table of values, right? And this is called parameterization. So we're parameterizing the ellipse. So we're getting x as a function of the parameter theta and y as a function of the parameter theta. And this theta is at 0. Where are we? This is 5, and this is 5. So we're starting out here. So this corresponds to theta equals 0. Right? And then as theta goes to pi over 2, cosine is 0, so this is 3. Sine is 1, so this is 8. We're at 3, 8. That's this point up here, right? And theta here is pi over 2. Yeah? And what do you suppose theta is here? It's going to be pi, right? If theta is pi, then cosine is -1. This is 3 minus 2 is 1. And this is 5 plus 0 is 5, right? So we're at 1, 5. Oh, sorry. Yeah, 1,5, right? This point here. Sorry, 1,5. That's theta equals pi, and 3 pi over 2 will take us to the south pole of this ellipse, where cosine is 0, so this is 3, and sine is -1, so this is 2, and we're at 3, 2, which is this point here, right? So this is 3, 2, where theta is 3 pi over 2. And guess what? At 2 pi, we're back home. So back to where we started at 5, 5, right? And that's once around the ellipse. And that's pretty powerful stuff there. You can do some serious math by parameterizing your conic section. Oh, we're out of time, huh? So any questions before we adjourn for the weekend? I'm going to be in the Math Science Study Center this afternoon between 2 and 4. Let me see, where are we?
I just think that's crazy how everything is like it all connects, like everything with cosine and sine and how we graph it, like it's all I don't yeah, it's just
I agree. This is kind of a nice moment where we're bringing together, maybe even the geometry of this thing, right? We got some right triangles in there, and bringing together the algebra, an equation involving x and y. What about functions? Well, x is a function of theta, y is a function of theta, so there we have our functions. Can you get y as a function of x? Well, it doesn't satisfy the vertical line test, but the upper half does. So when you go to solve for y, at some point you're going to have to decide, do I want the positive square root or the negative square root? If you pick the positive square root, you got the upper half of the ellipse. And if you pick the negative square root, you got the lower half. All right, well, on Monday, we'll take up from there. Yeah, and we'll try to wrap up chapter 11 and then do some review. Can we go over 14? I'm sorry, I didn't see that. Which 14? On the homework? Let me take a quick look at that while we're here. So that would be not here. Here? Number 14 here? Oh, what's going on there? Points A and B are separated by a lake. Find the distance between them. So this is a side angle. Oh, sorry, angle side side, huh? So that's the ambiguous case. But we do have a ratio. So let's, yeah, I'll do that. I know class is kind of over, but we can still solve this problem if you're interested. So let's crank it up. I'll draw it on the workbench here. And essentially we got this triangle here. And this is just schematic. It's not meant to be to scale or anything. This is 528 meters, I guess, 325. And this is a 48.3 degree angle. So angle side side. So we know that, let's call this A. So we want to find little a, right? And let's call this B and C. So we know that A over, I guess, yeah, we don't know either the angle A or the side A. So that we don't want two unknowns here, right? So we can find B though, right? So we can say sine B over B, which is 325, is equal to sine C, which is 48.3 degrees over 528. That we can solve for B. So B is going to be the angle whose sine is 325 over 518, or is it 528? times sine of 48.3 degrees. So that's a little calculator problem. So we turn on the calculator and do that. We're in degree mode, I think. So 325 divided by 528 times the sine of 48.3. And that's going to be the sine of beta, so we want the inverse sine of that. And that comes out to 27.36 degrees. Let's store that into B, right? So we can have that available if we need it. So store into B. Okay. So now we can say that A is 180 degrees minus B minus 48.3. And so let's store that into A. Really? I guess so, huh? It's an obtuse angle, does it? Doesn't look like an obtuse angle, huh? But that's not to scale. Yeah. So the diagram is misleading, right? So in fact, A is going to be approximately 104.34 degrees. Okay. So now we can find A, right? Because let's write it here. A over sine A is equal to, should we just use C over sine C? And so A is equal to C times sine C over, sine A over sine C. And on the calculator, I'd write C, which is 528 times sine A divided by sine C, which is 48.3. And that's a number, 685. Yeah, well, it's the opposite, the obtuse angle. So it's going to be the largest. So that's 685.1363, if you want 4 digits then. So let's see if that doesn't work for us. The other digits for good measure. Yes, okay. Well, I hope that's what you wanted to see. Yeah, there's some good ones here, no doubt. Yeah, if you have requests, let me know. We'll work together. All right. Well, let's end it there. Have a great weekend.
Thank you, Professor.
You bet. Nice being with you this week.
Thank you.
Next week will be our last week of classes and then the final exam. So that's why I'm sort of rushing to wrap this all up in a nice bow. All right. Ciao for now.